Test. All right, good morning, everyone. Welcome back. Today is the last day of this wonderful discussion meeting. After some technical issues, it's my pleasure to introduce the first speaker of this morning session, Nelli Litvak from the Technology University of Eindhoven. And she will be talking about detecting geometry in complex networks.
Yes.
Please.
Okay, where should I put this one? All right, so who wanted to finish their breakfast? I gave you enough time with all technical problems that I had out of all people. Now, hopefully slide will appear now and then we can start. Yeah. Yay. Yay, we managed. Okay. I think so, no? Yeah, can you hear me well? Yeah, I prefer to present with microphone actually. Yes, thank you. All right. Yes, thank you. Okay, all right. So we are coming to the end of this wonderful meeting that we all enjoyed so much, and everybody is tired from many fantastic talks. I will not put too much pressure on your cognitive capacity. I hope it will be easygoing talk for Friday morning. Okay, so basically I'm going to talk about detecting geometry in networks, and this is joint work with Ricardo Michelin and Clara Stegenhaus from the University of Twente. I did this also when I was in Twente. I switched to Eindhoven only recently. And so let me start with this. So we all we have heard many times that networks have this very heterogeneous degree distribution, right? And this is a picture that I like. I hope you can see it. It's a white points, and in fact, these little lines are arrows, but you can see that. So this is a network that my student made some time ago, and this is a tweets and retweets on the topic of Project X and Haren. And what happened at that time? At that time, Facebook was still used by teenagers, and one girl posted her birthday invitation for her 16th birthday on Facebook and forgot to set it on private settings. So this invitation got public and got viral. And on this day, 21 of September, a couple of thousand people showed up in this very little village near Groningen called Haren, and basically trashed the entire place. And we looked at the retweets and how it developed. So this is already when we can see that there are some people who get retweeted very often. So there are these dots here are the people who tweeted Twitter accounts, and the arrow goes if one person retweets another person. And you see already that the stars appearing, people retweet it a lot. And in fact, you almost all see only the stars. But if you look at people retweet each other more often, like there are many ages in this graph, but this one's most noticeable. And of course, the next day after that party, so this is the morning of the event, and the next day morning it became this. Much denser graph, but we can see still this star appearing. So this power law is something that we want to have in our network models. Then, so we model it using the so-called scale-free networks. Many people already mentioned that. And you can explain this in a different way. You can say, okay, people are popular, and more popular people become more popular. It's like preferential attachment idea. You can say, okay, people are like born with certain charisma or fitness or whatever you want to call it. So they are more attractive. Some people are generally more attractive than others, or some vertices generally more attractive than others. Some papers generally better than others. You can also say that there is a position, it is a position of the vertex that makes the vertex important. So this degree can be proxy for many things. And this Paolo degree distribution, we plotted this log-log plot, and we model it like this, that the probability of the fraction of vertices with degree k decreases as a power of k, and we usually have this tau between 2 and 3, which means that we have a final mean and infinite variance. So that is what we saw already many times. I just a little bit refresh so that I can fit it in my talk. So scale-free networks, then, like, once people figured out, they appeared everywhere. And I think Remco already mentioned that there is a debate going on whether this Paolo really is a right model, so whether real-life network actually are Paolo or not exactly, or maybe they're log normal or whatnot. Well, to be honest, so this is also a very nice exchange of papers. So Clausette wrote this paper, scale-free networks are rare, and Remco and Pim and Dima Krukov, Ivan Vitalov answered with scale-free networks, well done. Basically, point is that you may say that Paolos are generally there. You may say they're not there. You may say that it depends who you ask. You may say they might be there, but we will never be able to figure out. I think that was the stretch of Pim's and Remco paper, that there is no way to figure out whether they're there or not. Okay, but they're a good model because they capture heterogeneity, and that's why they're an interesting model. Okay, so now very popular model is this inhomogeneous random graph. So you can call it also Junlu, or you can call it soft configuration model. There are many names for this. And this is an undirected graph with vertices from 1 to n, so this n parameter. And we assign each vertex a weight. And we say that these weights will be distributed with this Paolo. And here I use the cumulative distribution, the tail probability. So that's why it is not a fraction of vertices with weight y, but fraction of vertices with weight greater than y. And therefore we take cumulative probability, and this is not then y minus tau, but 1 minus tau. So +1 because of integration. And when we say we connect vertices I and j by an h independently with this probability, so if the product of this, so mu is the average weight, and this is like a usual normalization. And if this product happens to be larger than n mu, then we connect this to vertices probability 1. So this is how this model works. It is a very standard model. All right. So then how it looks like, so we have these vertices, and then vertices get some weights attached, so that they are kind of different size, and then the bigger ones that they have high chances to connect to others. So the probability to connect is proportional to the weight. So, and that's how we create a network which has this Paolo degree distribution. Now, we know a lot of things about this, like, for instance, if we denote by di as degree of a vertex I, then average degree will be, so expected degree will be, with some correction, will be equal to the weight. And we also know that in the limit, these weights will have Poisson distribution. And we know that the probability that the degree is greater than y will also converge to this with some correction. So basically, the behavior of the degree will be very similar to the behavior of the weight with some correction. And we also know that local limit is a 3, and local weak limit was, let me take a little bit popularization role here. Local weak limit was mentioned many times. When I was visiting last year in this Simon's Institute, then I was talking to students there, and one PhD student, they have created this website. It's called Spectral Collective. It's a YouTube channel. And on this YouTube channel, they explain difficult mathematical concepts with animations. Who knows 3 blue, 1 brown? Yeah, many people. So there is a wonderful website, 3 Blue 1 Brown, where they animate mathematics. And this person who runs this website makes the software available and runs this type of competitions or events, and people can use the software to make their own animations. So the students did this and created a wonderful animation about local weak limit. So if you ever want to explain it to the students, then you can go to see this video. But my topic of my talk is not local weak limits, so I will not go into this and into the video. But in any case, so local weak limit of this graph is a 3. So we know quite a bit about this graph. Okay, so this is a Paulos, and now if you look at this graphs, then they will see that so in this case, like also looks like stars. But we also know that in real life networks there are a lot of triangles. That there is a tendency for triangle closure. So if A knows B and A knows C, then B and C tend to know each other as well at some point. So we usually observe many triangles in real life networks. So, and we can count triangles. I mean, for us, for probabilists, it's very easy to count triangles. I have counted them already. I just wrote my sum of indicators, I'm done. Okay, I have been at a conference of computer science where I met people who basically make their living from counting triangles. Because if you really want to count them, the complexity, polynomial complexity is very high, and how you approximate it well. And there is a whole bunch of research about how to count triangles. Okay. Another way of measuring this triangle closure is this clustering coefficient. And for scale-free networks, it's actually better to use local clustering coefficient rather than global. I don't have this reference here, but powered lower degree distribution basically kills the global clustering coefficient. So local is better. So the local clustering coefficient is this, is just simply you count, you look whether how many triangles the vertex is involved in, and you divide by the total number of pairs of neighbors. So basically it's a fraction of the neighbors of the vertex that form a triangle. Okay, so these are very well known things in networks, like we already been doing it for really long. And then when we want to reflect on triangles, then really we look at different type of models. We look at geometric random graphs. And geometric random graphs means that vertices are located in geometric space, and then they connect when they are close to each other. And that's, of course, is very natural creates triangle closure, because then if A is close to B and A is close to C, then maybe B is close to C, so we have a high chance of creating a triangle. So geometric random graphs, they reflect that property. And actually this geometry in real life networks is very meaningful. So now I will show you some pretty pictures. This of course comes from the original paper about hyperbolic random graphs. So this is where they introduced hyperbolic geometry, where you can also create, you have a geometric graph which also has a scale-free distribution. And basically the number of neighbors depends on where you are in this space. So this, if you are closer to periphery, then it is kind of equivalent to low weight. So basically you have very small number of neighbors in your neighborhood because it's curved space. And if you're closer to the center, then you have like bigger, your radius effectively includes more vertices, and that's how Paolo is created. But also in real life, so this is the very famous OPTA project where they visualize connections in the internet. And these colors actually represent continents. And it's very hard to see anything from this visualization. You can also visualize it probably differently, but clearly internet routers also are located somewhere. So geometry is generally there, just geography. And geometry can be something completely else. So this example is just geography, right? But for example, this fish is a sample from a website, from a collection from the website that basically is a web crawl that my postdoc made. And here, these vertices here are the web pages, and the lines here are the connections between the hyperlinks between web pages. And their geometry is something else. Geometry is the content of the web page. So in our case, this was like this dots, this is a projection, but actually each web page had 192 coordinates based on its content. So they were effectively positioned in 192-dimensional space. And we figured out that indeed this closeness and this geometric space was very, very meaningful also for connectivity and for prediction of what will happen next. Okay, so, and there is also yet another interpretation of geometry that is very important nowadays, which is related to machine learning. So you may have a network which has no geometry at all, and yet it can be meaningful to embed your vertices in a geometric space artificially. And one very famous algorithm for that is Litvak by Leskowitz. And this basically what it does, I will not explain how it works, but it basically it runs random walk, which can go back, which can go explore back and can go explore forward, and these parameters tune how much forward exploration you have and how much backward exploration you have. So basically they take into account last two steps, and then they run this random walk. And they create like sequences of visited vertices, and they interpret the sequences as like sentences. So like every vertex is a word in a sentence. And then they use this, what's the same thing that they use in language models to embed these vertices on in geometric space based on how often they appear close to each other in these strings of random walk. And then they create geometry. So then the network is placed in geometry, and that is also very meaningful. For example, they use this technique for, I think, for link prediction and for community detection. So that you can do many tasks on networks using this geometric embedding. So even if you don't have geometry, sometimes you want to make it. Okay, so now the problem is that assume we have a scale-free network.
So the word embeddings that they use in transformers, where each word is 2 raised to the power 700 dimensions.
Yeah.
Model at all?
Yeah, I think transformers, I do not know, but I know that the language model, they embed words, like based on, so they basically crunch parse gigantic amounts of text, look at the sentences of particular length, and then they create a model like which word has to follow another word based on this text. And that's how they, so basically their model is based on coordinates, and then they feed the coordinates that explain the text the best. And I think, if I'm not mistaken, automatic translation has approximately 1,000 dimensional space for the words. So you see, words originally don't have any coordinates, but turns out it's very good to give them coordinates. But okay, back to our network. So basically, say you have a network in the sense that you have a adjacency matrix, or you have a list of ages, basically completely like neutral information, like the way we have it usually in computer. And now the question is, did geometry play a role in creating this network, right? Did geometry play a role? Can we model it without geometry, or should we model this with geometry? And what people often do, yeah, so actually this problem falls under the category, in my opinion, of model selection. And that means that is basically, on a broader way, it is the following problem. Assume we have a network, so which model created it? This is one of questions that Remco also mentioned during this discussion. How do we select like the best model? How do we know which model created this network? So there is some research on this, but not too much, but some. And for instance, here they use kind of machine learning method, and it was funny because they kind of looked at a little bit of a negative side. So they basically they said like this: if my classifier cannot distinguish the network from the model, then my model is good. So basically, if my classifier is wrong, then my model is good. But of course, a lot of, like, immediately on real life networks, all models are rejected. So it's an ongoing topic. We now wrote also a paper about distinguishing these different mechanisms, preferential attachment is currently under review. So I think that answering the question whether geometry was there or not is a meaningful question, and it falls under this category. Which model to use to model the network?
So can one think about, you can take any network and embed it in a very large dimensional space. So really, if the smallest space that meaningfully embeds a network, that's it.
So yes, you can embed network anywhere, but basically sometimes you have genuine geometry, like for instance location or content closeness. So when you just see the list of edges, was geometry there? Were they, for example, these triangles, were they induced by geometry or not? That is basically what we are trying to do. So okay, so now we can introduce model with geometry, which is basically also this hyperbolic model. It can be seen as a part of this model. So, and the model with geometry weights are again there, but now the probability of connection will depend also on the distance in a particular way. And we normalize it so that the degree is again approximately the weight. So the average degree again is approximately equal to the weight. Okay, so so here you see this was still there, and this depends on geometry, and this is the parameters, the dimensions, number of dimensions, and this gamma parameter. Okay, so now we have again vertices in the space, and we assign weights to them, but now they are connecting not only by weight but by closeness also. So for example, here, see here, and here you see already triangle appearing. Okay, so these are the two models. I hope that was clear. So one is this inhomogeneous random graph, which we call IRG, and another is a geometric inhomogeneous random graph, which is called GIRG. Okay, so these are the two models that we are going to talk about, and there are differences in this red term. Yeah. Yes.
What is the assumption on X here?
On which X?
The coordinates.
Coordinates. Yeah, they're just in some geometric part of geometry. So you can say on 0, 1, like to the power d.
But later on, will you try to fit to these coordinates, or do you?
I will tell you what I will do later on. So wait. Okay. So now properties that we know. So we normalize this in such a way that average degree is approximately is again the h. So then the degree is still Poisson, and yeah, and this basically all these properties hold. And also asymptotically, when you take d is 1, and this is what we actually did, and then if you did d is 1 and let gamma grow large, then it is equivalent to hyperbolic geometry. Okay, so now these are the two examples. Can you see which one is which? It's not very easy to see from visualization, right? So this one is without, and this is with, and when you zoom in, you will see it. So here you basically don't see triangles, and here you see triangles appearing. Okay. So now, now basically what people do, that I already said, so to detect geometry, they look how many triangles we have. And that's the most natural thing, right? If there are many triangles, then geometry was there. If there are not many triangles, then geometry was not there. But actually, if you look at the graph without geometry, then you also have triangles when you have power laws. And that is a very important point. So if you take Erdős-Rényi graph, then the number of triangles will be basically finite in an infinite graph. So it means that you almost cannot find them. But if you have a power law, then the picture changes. The picture changes. And this result is a very nice result by Clara and Remco and Johan van Leeuwarden. And they got this result using so-called variation method. And this is very, very nice method. So I will take the liberty to explain how it works, like why this weird number, why so many triangles in this inhomogeneous random graph with exponent tone. Okay, so here how it works. So this, suppose we have a triangle I, J, and K. And what we do, we kind of parameterize it, not we, but in this paper, what they do, they parameterize it by power of n. So if alpha is 0, then it means that your weight is like limited. But if alpha is alpha here, if alpha is say 1/2, then your weight is approximately n to the square root of n, right? And alpha can be between 0 and, who knows? So, so basically I say my weights are distributed according to the power law with exponent tau, okay? And I parameterize my weights as n to the power alpha, all right? So alpha obviously can be 0, then my weight is some constant, right? But if you take all the possible weights, like imagine this can be like, for example, the highest, the maximum of n weights. Do you know what this maximum alpha will be? Somebody knows? Now this, so 1 over tau minus 1, that is the highest weight out of n. So it will not be constant, but it will be growing. The maximum will be growing with n, and the maximum will grow as this power of n. Okay, so now let's look at how many on average triangles we have. And this is a very loose explanation of this variational principle, but basically these are the number of triples with such weights. Why is that? Because these are the probability. So this is the probability of having weights like this, right? N minus, so because weight is n to the power alpha, and then we have to take this weight to the power minus tau, so this is this part. And if you want to know how many vertices of such weight, we have to multiply by n, each of these probabilities, so multiply by n to the power 3. And these are the probabilities that they form a triangle, right? And I would say, okay, it is like probability is n to the power alpha I times n to the power alpha j, but don't forget this one, because we are talking about powers of n. And if alpha is greater than 1/2, which it will be if tau is between 2 and 3, then this actually this product, if both of them are very large, this product actually will be greater than n, and then it will be 1. So that's why when that happens, then we have to take power n to the power 0, right? So then this is the probability of them forming a triangle, and then you can say, when is this number maximal? And it turns out that this number is maximum, then all vertices have alpha 1/2. So the vertices of degree square root of n form triangles, and that is very natural because they have probability, like in geometric networks, they have just positive probability of forming a triangle. So they will form a lot of triangles. In fact, in the configuration model, the highest degree vertices form a clique, like in the middle of the graph. So they will form a lot of triangles, and how many triangles they will be, that's exactly that number that I showed to you before. Okay, so that is the derivation. So the bottom line is, if you have a power law network, even if it has no geometry, it can have quite many triangles. Okay, now let's look at the model with geometry. This is just a reminder how model is made, the same, but here with this geometric term. And now we have these triangles, and we know how many. And we have also the same triangles here. Yeah, and we have also now new triangles, which are the pink triangles. These are triangles created due to geometry, not due to the large degrees. Okay. Okay. So, and now turns out that the number of these blue triangles here is exactly the same. But what about the number of these pink triangles? And now I want to check your intuition. And I'm going to go to this website. I hope it works. No, sorry. Oh, but where is my website? Ha, ha, ha. Yeah, wait. Yes. Yeah, I think I have it here. Yes. All right, so my university used this Mentimeter tool, and I'm going to quiz you now. So how many triangles, pink triangles, do you think are there? You can go to this mainc.com and use this code and try to answer. So will it be order 1? Will it be order n? Will it depend on parameters, all parameters of the model, or will it depend only on geometric parameters of the model?
Sorry, what is your definition of pink triangle again?
Pink triangle are the triangles that, so basically we have two triangles, two sort of triangles. Some triangles are created because the vertices had such a high weight that they created a triangle. And the pink triangles are triangles that are induced by geometry. So they appeared because the vertices are close to each other.
So even when the degrees are small?
Yeah, even when the degrees are small. Yeah, even when the degrees are small. So let's see whether we have any answer for now. Okay, we have some answers. Let me hide the answers. I'm very good. You know, this is also how I do my teaching. I don't like to lecture because then I mentioned this. I visualize this. Suppose everybody had the red button, which they switch on when they stop following, and I'm just terrified of when I imagine the number of red buttons that will go up at the second half of the lecture. So that's why I don't do this. So I do this in an interactive way. So let's see. 7 people already answered. So let's see 8. Let's wait a little bit longer. Somebody else want to answer? 10. Okay, fantastic. Let's see the results. Okay. Wow. Okay. Okay. So you see, it's not that simple. It's not that simple after all. Let me see if I can show you the correct answer. I forgot how to do that. Yeah, press enter. Yeah, indeed. Yes. So it will be order n of these triangles. Let me go back to my presentation. I hope I can. Somehow this computer is not my friend. I think this is my presentation. Yeah. So yeah. So this number of these triangles is indeed order n. And why? Because, like, think about it. Like, there is a vertex in a neighborhood, okay? And with positive probability, triangle will be formed between vertices that are nearby. It will be just finite positive probability. And for every vertex, it will be true. So on average, there will be a linear number of these triangles formed due to geometry. But what is interesting, that when tau is smaller than 7/3, then this number is bigger. So when your power law is really heavy tail, right? And that is like 7/3 is between 2 and 3. So if it is really heavy tail, then suddenly the triangles formed due to their high weights, they start dominating. And when you count your triangles, you will not see the difference between geometric model and non-geometric model. And yeah, so that is basically the main message. And then how can we avoid it? How can we avoid it? And then basically think about it. What is the problem is that too many triangles formed by very high degree vertices. So somehow we want to discount those. And that is the main, basically the main idea that I wanted to show now. So we can detect geometry when we discount these large triangles, and we can do it by introducing a new statistic, which we call weighted triangles. So what we do, we count these triangles again, but we divide each count of each triangle by the product of the degrees of the 3 vertices involved. Yeah. So then what happens is these blue triangles had very high degrees, but we divide by these high degrees, so their contribution becomes very much less. Okay. So so now what we want is that our number of weighted triangles in the inhomogeneous random graph is of a smaller order than the one in geometric random graphs. So basically, if you go back to the picture, then you can see in geometric graphs, these triangles will have usually low degrees, so they will have higher contribution. But in inhomogeneous random graphs, basically all triangles are of this nature that they high degrees, they will have high degrees, so this statistic should become small, right? So so basically what we want then, how do we want to show this? We want to upper bound the weighted triangles in inhomogeneous random graph, and we want to low bound the weighted triangles in geometric inhomogeneous random graph, so that we can say that, okay, the lower bound of this is always bigger than upper bound of that. That's basically the idea. And this is the first step. So we want to bound this. Well, to be honest, in this particular paper, which is published in Physics Review E, it was not, we didn't bother to go very, very precise. So in that sense, there is a little bit of cheating. So because instead of analyzing this, we analyze this quantity, which is the same, but we replace triangles by weights. And since the degree is close sufficiently to the weight, then it should be the same, but we didn't really prove that step. We just said, okay, let's look at this proxy. Okay, so now upper bound of this. So everybody understands this, right? So we are talking about this quantity, right, for inhomogeneous random graph, right? So we did this to kill the triangles. Now my question to you, what do you think how successful we were in killing these triangles by dividing by the degree? So that is my next question. So when we bounded this, what do you think became an upper bound? And my my possible answers are, yeah, I'm sorry, this computer doesn't like, I think, am I in the right place? Yeah. One more, yeah, I know, but it's not, yeah. Okay, so let me go to the next one. I should go to, yeah, here, I can go to the next one. Yeah, I still have to get used to it because Twente was using something else. Yeah, okay, so I give you three possibilities. Like one, we kill triangles reasonably successfully, so now the number of triangles is n to the power epsilon. Another is that we could bound it by a constant, and this constant was terrible. And another one, we could bound it by a constant, and the constant was 1/6. Okay, so let's see what we're getting. 6, 7, let's wait a little bit. 8, who gives me the 8th answer? Yay. Okay, no. Okay, let's see. Let's try to see what we are getting. Oh, okay. Good. So let's see what the right answer is. Yeah, it was 1/6. We were surprised. I mean, we were surprised. Okay, let me now go back to my presentation. Okay, all right. So I will not quiz you anymore. Don't worry. So now so this bounded by 1/6. Oh. Yes. Oh, that's. If you don't like it's how you define terrible. Yeah. Okay, good. Oh, you're laughing. I'm so happy. Okay. So yeah, and of course, when we want to lower bound, I think there is no surprise for you that we will lower bound by what term? Like what order of magnitude will be the term for the lower bound? What? For the lower bound of geometric graph, what will be the, say, when we want to lower bound? So this is our goal. So we upper bounded this one. Now we want to lower bound this one. And what is the order of magnitude of lower bound for this one will be? Recall this. Yeah, recall this. That number of these pink triangles was order n. So basically nothing changed. So we could bound it by order n from the below and terrible constant and the terrible constant. Yeah, and the terrible constant. Okay, so basically, and we also did some concentration. So we also showed that the variance of this thing is also order n. So basically, we have it concentrated, and it means that it is indeed, this quantity is indeed order n. So then this quantity gives us hope to find out whether there is geometry or not. And these are some pretty pictures that Ricardo made. So these are TOR 2.9. right? So, and this is 2.1. And remember, there was this threshold 7/3. So this one is above threshold, and this one is below threshold. And what we see is a number of triangles. So here you see they grow like basically the same. This is a number of triangles, but you can see a little bit the difference. But here, when we have a very heavy tail, and by the way, this, for example, what they have seen in the original study of the Paulos and World Wide Web was exactly that exponent 2.1. And you see very often this exponent is very close to 2. And for those, what you see is that this is what you see when for different network sizes in homogeneous random graphs. And this is what you see in geometric and homogeneous random graphs. So they both grow linearly, not linearly, but they both grow as the power of n, and you really cannot distinguish between the two. But now when we take weighted triangles, they behave much nicer because the weighted triangles without geometry, they are bounded, and with geometry, they grow. Yeah, so of course, you can ask many questions, like, for example, what the reviewer asked, that you need this to apply it, you need a sequence of networks, right? Because you have to see how it grows with n, and that you don't always have. And yet we could apply it to real life networks. Okay, yeah, and also let me also say about local clustering coefficient. So that local clustering coefficient also often used. And if you do it in a classical way, then it already has some degree discount, actually. You can rewrite it this way. But you see here, for example, if one of the vertices has small degrees and the others are too big, then still this triangle will contribute somewhat. So that is less effective than weighted triangles. And when we see the experiments, then indeed, like in these cases, like this is local clustering coefficient, when Paulo exponent is above 7/3, then you can see clustering coefficient in geometric networks behaves differently than in without geometry. But when your Paulo exponent is high, then clustering coefficient behaves exactly the same with and without geometry. And when we take at weighted triangles, like weighted triangles, then these are the same pictures. Then you see we can distinguish it very well. So basically, this statistics helps a lot to find whether geometry was there or not. Okay, so now we also applied it to some real life networks, and we chose the ones where we can track the change in size. That was important. Because this is how we check the geometry. And these are the results. And arguably, you can say that each of these networks has some geometry, should have, because collaborations means like people who are close to each other topic-wise. And these are internet routers, and they could be by internet protocols, so by geography, they could be close to each other, and this peer-to-peer connection, similar things. So basically, all these networks kind of naturally include geometry. And when we look at number of triangles, then it's a little bit of a mess. And when we look at clustering coefficient, also doesn't say much, but you see weighted triangles actually behave very nicely. When n grows, then they grow linearly for real life networks as well. So that is very nice. Okay, so now you see, despite of technical difficulties, I will finish early and will be time for questions or coffee, which is probably not bad for Friday morning. So, but actually, we kind of stopped there at the point, but we wanted to go further. And of course, because what you really want, these pictures are promising, but this is not a statistical test. So ideally, we would like to have a test where we can say, okay, if your weighted triangles are like of this order, basically we want to have some test statistics to see when we can say geometry was there or not there. And the good candidate probably is square root of n. So look at the order of square root of n, but that's the question is the problem is that order of, because in statistics, of course, they should be order n should be multiplied by some random variable with known distribution, and that we don't have, right? So, so that is still an open question. I'm not sure how solvable this question is. Probably we could make some progress, but I really don't know how far. And yeah, it's not clear. You know, it's also Yes, absolutely. Yes, it's quite hard, but we already cheated like by doing weights instead of degrees. And in the real life, you will have degrees that will add more fluctuation to this.
Yeah, because the weights are
yeah.
but the degrees are not.
Yeah, and also you see this constant, we really cannot say much about it. Like it looks like all these constants are small. I don't know. It's like it's really not clear. This 1/6 is very serene example. So for real life networks, it will be.
If you would do the weight triangles and not weight weights are observable, would you get similar results?
I'm sure that if we divide by that we can analyze this.
But you do this here, right? Here you divide by.
Yeah. Here we divide by degrees. Yeah. So I mean, I'm sure that if we analyze properly these weighted triangles with degrees instead of weights, we'll get the same result, just with a little bit more trouble. But also 1/6 is very much related to the exact definition of the model. We use a particular relation between D and gamma, so that everything is like, but what we want ideally is to say whether the geometry is there or not, despite of all these little parameters. So it's not very clear how to do it. Yeah, and then maybe we can do it for a broader class of geometric and non-geometric models. And you know what? When we look at the data, it looks like all real-life networks have some type of geometry. So that is also a question. Can we find a real-life network that doesn't? That generally doesn't. I don't know. Maybe it can be sub-network of something. I don't know. Where homogeneously enough sub-network something. Yeah, and maybe even one statistics is not enough to really say whether geometry played a role or not. And maybe some machine learning has to be used for that, I don't know. So, but at least I think the statistics can give some indication, and that's already, I think, is very nice. So that is the reference for the paper, and I thank you for your attention.
All right, thank you very much for this wonderful talk. Questions? Yes.
Thanks a lot, Nelly. Very, very nice talk. I have one question. So since this test is not based on any measured coordinate, right? So the test itself, this W, only looks at the topology.
Yeah.
So what you see in these three examples of real networks is that you have a superlinear growth, a non-constant, sorry, a growth of W where you would expect it to be constant if it agreed with the non-geometric model, right? But from that point to say imply that what is missing is necessarily geometry, I don't see whether it's a unique, implication. For instance, could it there be that the links are created with a model that has dependent edges, so that there are, I don't know, hypergraph where you have dependencies between edges that might result in more triangles than you have in edge-independent graphs, but not necessarily geometry in the sense you are discussing at the beginning.
Yeah, it is a really excellent point, actually. So the way I view it is this. So we have a network, we want to model it. How? So included geometry is one way of modeling dependency between edges, very elegant one. Otherwise, you have to do, say, okay, if I have edge here and here, what's conditional probability to close the triangle? So geometry gives you this. So in some sense, I do not see contradiction. So maybe networks with dependencies are actually well modeled as geometric. But you're right that geometry doesn't mean real geometry in a proper space. That's why I gave you all these examples at the beginning. I mean, the words don't have geometry, but we come up with geometry because we want to do automatic translations like this. That is what I also say at my first year, like first class on linear algebra. Say, like multidimensional spaces are extremely useful. Sometimes you want to have multidimensional space even for the objects that don't have any coordinates or any numerical characteristics, such as words. So here is something, I believe something similar. So assume you have network with a lot of dependency, but how do you model it best? And maybe geometry gives you a means for this, even if there is no actual geometry in it. Yeah. Yes?
Yes.
So this might be related to the last, to part 4. Did you look, for example, into, say, the difference between degree correlations in these two models? Because when you have geometry, right, then there's a larger fraction of common neighbors. So you would expect these networks to be, say, assortatively mixed. While all of these others, as they are locally true-like, you would expect them to be at least asymptotically, sort of neutrally mixed. Did you look into this?
No, we didn't look, and actually that's a good idea. We didn't look at degree correlation in this, but
you might get a similar problem, right? Because it's all asymptotically, right? So you might there might be some sort of scaling there that you need to do as well. I don't know, but
yeah. But as you know very well, these big power law networks, which have simple graphs, are usually like disassortative.
But then it would be even better because the others should be assortative.
Yeah. I don't have an answer to this. I mean, we didn't look at it, but it can be a good idea. I think so. But what can be a problem there is that assortativity is generally about 2 vertices connected to each other by an edge, right? And here it's generally about 3 vertices. So I'm not sure how to make it like this 3-sided relation in terms of degree relation. But maybe it is good to, for example, look at maybe I can look at assortativity between 2 vertices that are involved in a triangle. That is possible. Something like that. That probably could be useful. Yeah, that could be useful.
Any other questions? A quick question from me. Have you thought of going to higher cycles? Because when you look at this, these graphs, like in my talk, I've shown that you have usually, if there's cycle dependence, I mean, there's more cycles than expected. It's usually triangles, 4 cycles, 5 cycles, so it goes up. Have you thought about doing more higher orders?
Yes. So first of all, like what is hidden under the rug here, that at the end of the day, you do have to count triangles. And that is already a problem, like because triangle count, if you do it in a naive way, has polynomial complexity, which is kind of unacceptable, right? So with cycles, it will be even more difficult. And another thing is that, so this, for example, what I showed, this variation method that Clara and Remco and co-authors developed, that works for any pattern. Not only triangle, but you can do cycle, you can do any finite graphlet and define like which of them are most common, and then you will know how many of them will be there. So in that sense, I don't see why this cannot extend to cycles. Probably it will be, but I'm not sure it will be very useful. So counting cycles will be more difficult, and whether they will give more information, I'm not sure. Also in models without geometry, at some point you start seeing cycles. So after approximately logarithmic number of neighbors, you start seeing cycles. And a logarithm is a function which of course is very slow. So one of the problems when you apply it to finite networks like of 1,000 vertices, then logarithm can be already like, I don't know, 4. And then it is a 4 cycle. You know, and then you have another problem. Like, did I already hit my minimum distance with this? So that's why I think triangles. I would probably stick to triangles, but I think it is also a good question. We could look at other graphlets or cycles. Yeah.
Okay, so let's have a break for 10 minutes, and let's thank the speaker again.
Thank you.